So let's look at our units. If you look at your equation, P equals nRT. Okay, it's RT over V molar volume minus B minus A times 1 over molar volume squared, right? What's our unit for B? B has the same unit as molar volume. Remember, it's excluded volume. So if you look up values for the van der Waals constant B, it's given in liters per mole. Okay? Let's compare the B value for O2 versus H2. This is 0.03186 liters per mole for O2. For hydrogen, it's 0.02665. Why is that? Which one's bigger? O2. Why is the B value bigger for O2? What's B and what does B tell us about the molecule? The size of the molecule. So O2, an O2 molecule is bigger than a hydrogen molecule. Okay? So on a test, I should be able to ask you questions like that. If I were to ask you, okay, C6H6 versus CH4, which one has a larger B value? C6H6 is a bigger size, right? So B is a measure of the molecular size. In fact, B, we say, if you were to assume your molecules are spheres, it's 4 times the volume of the sphere, okay, of a mole of spheres. Okay, so you can estimate, if you can imagine your molecule as spheres, you can estimate the size of those spheres from the excluded volume. Now, what about the van der Waals parameter A? What's the unit for that? Okay. A times 1 over Vm squared must have a unit of pressure, right? Because pressure is equal to this minus that. So A over molar volume squared must have units of pressure. So how can that have units of pressure? What's the unit for molar volume? Liters per mole, right? So you square that. So what should be the unit for A so that the whole thing becomes a unit of pressure? It's a pressure unit, so something like atmosphere over liters per mole squared. Oops. Times liters per mole squared. Okay. Oops. It's atmosphere times liters per mole squared, so that we can cancel liters per mole squared and you get atmosphere. So the unit is a pressure unit times liters per mole squared. Okay. A bar is a unit of pressure. So how is a bar related to an atmosphere? 1 atmosphere is 1.01325 times 10 to the 5th Pascal, which is a Newton per square meter, remember. And 10 to the 5th Pascal is what we call a bar, so 1 atmosphere is 1.01325 bar. Okay, so let's look at these numbers right here. C2H6 versus CH4. Why is the value, the A, the van der Waals parameter A, larger for C2H6 compared to CH4? Why is this value bigger for C2H6? How does C2H6 compare to CH4? Bigger size, right? Bigger size, so bigger B value. But why is the A value also bigger? Attractive forces. What kind of attractive forces do C2H6 molecules have for each other? What do you call these molecules? What type of molecules are these? Polar, nonpolar? These are nonpolar molecules, right? The only type of attractive forces they have for each other are London dispersion forces. Okay? So what did we say about London dispersion forces? The larger the molecule, The bigger the region where your electrons are roaming around, the more polarizable, right? Which means that there's a greater you're gonna get stronger attractive forces. Polarizability means ability to form temporary instantaneous dipoles, right? So this one would have stronger attractive forces among the molecules as opposed to these smaller molecules. So in general, you'd say the larger the A value, the larger the B values, the larger the molecules, the larger the B values, the larger the A values. Okay? But what about water versus H2S? I think I have that right here. No, that's not water versus H2S. That's just H2S. Let's compare water versus H2S. H2O and H2S. Where do you find oxygen and sulfur in your periodic table? Group 6A, right? Column 16, oxygen is in second period, sulfur is in the third period. So, A or B, which one has a larger A value? And let's start with larger B value. Which one has a larger excluded volume, H2O or H2S? Okay. Which one's bigger? Going down a column, size of the atoms increases. So H2S would be a larger molecule. Sulfur is a larger atom than oxygen. Okay? So H2S would have a larger B value. Which one would have a larger A value? H2O or H2S? Which type of molecules would have much stronger attractive forces among them? That's another way of saying it, right? Remember, A value accounts for attractions. So for which molecules would you see stronger attractive forces? Intermolecular attractive forces. Among water molecules or among H2S molecules? Oh, 50-50, just about. Okay. Need to phone a friend. You remember what we said last time when we talked about intermolecular forces? Something about water being anomalous, right? What's the anomaly that's associated with water in terms of attractive forces? Water is made up of very small molecules, even smaller than O2 molecules, yet at room temperature it's a liquid, while as oxygen is a gas, right? H2S is a gas at room temperature. H2O is a liquid. Why? Because of hydrogen bonding interaction, you have an anomalously strong attractive forces among water molecules. Given that, let's see if you can, why don't you convince your neighbor your answer is correct and we'll redo the poll. Go ahead, you can talk. You ready to redo the poll? Okay. Which one would have a larger A value? Instant response, very good. That's water, has larger A values because of hydrogen bonding interactions. Okay?